21st February 1940. The basement laboratory at Birmingham University hummed with an unusual tension that morning as Professor John Randall and Dr. Harry Boot stared at their crude sketches spread across a cluttered workbench. Outside, Britain stood alone against Nazi Germany, and the nation's survival depended on a technological miracle that seemed impossible to achieve. The existing radar systems, bulky as railway carriages, could detect enemy aircraft from ground stations, but they could never fit inside the cramped fuselage of a fighter plane. What the Royal Air Force desperately needed was a device that could generate extremely short radio wave centimetric waves, with enough power to detect enemy bombers at night. Every scientist in Britain knew this was the war's greatest technical challenge, yet none had solved it. The two Birmingham physicists had been working on cavity magnetron designs for barely 3 weeks, operating under crushing pressure from the military establishment. Their supervisor, Professor Marcus Oliphant, had challenged them with an audacious goal: create a valve that could generate wavelengths around 10 centimeters with at least 1 kilowatt of power. Previous magnetron designs had failed spectacularly, producing either insufficient power or uncontrollable frequencies. The German Luftwaffe bombed British cities almost nightly, guided by darkness that rendered conventional defenses useless. Ground-based radar could track these raiders, but intercepting fighters flew blind, unable to locate their targets in the blackness above England. Randall, a theoretical physicist with wire-rimmed spectacles and a perpetually furrowed brow, had spent sleepless nights considering the fundamental physics of electron oscillation. Boot, younger and more experimentally minded, brought practical engineering intuition to their partnership. Together they conceived what their colleagues initially dismissed as an absurd notion. Instead of using a single cavity to resonate electromagnetic waves, they would drill multiple cavities around a copper cylinder, creating a structure that resembled a bizarre mechanical flower. According to established radio engineering principles, this design made no sense. Conventional wisdom suggested it would produce chaos rather than coherent radiation. Yet on that cold February morning, the two men possessed something more valuable than conventional wisdom. They had desperation sharpened by mathematical insight. Randall had calculated that if electrons could be forced to oscillate synchronously through multiple cavities simultaneously, they might generate unprecedented power at the exact short wavelengths needed for airborne radar. The geometry seemed wrong to experienced engineers, the concept too radical, the timeline impossibly compressed. Britain's industrial capacity was already stretched manufacturing Spitfires and Hurricanes. Adding a complex new electronic device seemed like wishful thinking. The Birmingham laboratory where they worked had been established only months earlier as part of Britain's frantic effort to develop centimetric radar technology. According to historical records maintained by the University of Birmingham archives, the initial research budget was laughably small, barely enough to purchase copper stock and basic machining tools. Randall and Boot would need to fabricate their prototype themselves, using whatever materials they could scavenge from university workshops. They had no team of technicians, no established procedures, no proven methods. They had only their calculations, their intuition, and the knowledge that thousands of British civilians died each month because fighter pilots could not find enemy bombers in the dark. The magnetron they imagined had to work because failure meant watching Britain burn. 6th March, 1940, and the machine shop at Birmingham University echoed with the screech of cutting tools biting into copper. Randall and Boot had transformed their theoretical sketches into precise engineering drawings, but now faced the brutal reality of manufacturing. Their design called for 8 cylindrical cavities drilled with perfect symmetry into a solid copper block, each cavity precisely measured to resonate at the target frequency. The tolerances required were extraordinarily tight. Errors of even a few thousandths of an inch would destroy the device's functionality. Neither man was an experienced machinist, yet they could trust no one else with work so secret and so urgent. The copper block itself presented the first challenge. Copper conducts electricity superbly, making it ideal for radio frequency applications, but its softness makes precision machining difficult. Boot spent hours at the lathe, carefully boring each cavity while Randall checked measurements with calipers, both men covered in copper dust that stained their fingers green. They worked late into the night, sleeping on cots in the laboratory, driven by reports filtering back from London where German incendiary bombs turned entire neighborhoods into infernos. The Luftwaffe's Heinkel bombers attacked with impunity after sunset, their crews confident that British night fighters posed minimal threat. While Randall and Boot machined their copper cylinder, parallel efforts were failing elsewhere. The research establishment at Bawdsey Manor, where British radar had been pioneered before the war, struggled with traditional magnetron designs that could not achieve the required power output. Scientists at the Telecommunications Research Establishment in Worth Matten tested klystron tubes imported from America, but these devices proved too weak for practical airborne radar. The British military's scientific advisor, Sir Henry Tizard, understood that the nation faced a technological bottleneck that could determine the war's outcome. Radar had already proven its worth during daylight raids, giving RAF Fighter Command the crucial advantage during the Battle of Britain. But night operations remained blind, and Germany was shifting to nocturnal bombing precisely because British defenses faltered in darkness. The cavity magnetron design that Randall and Boot were constructing operated on principles that seemed to violate established engineering intuition. In conventional radio tubes, electrons flowed in carefully controlled streams, their behavior predictable and well understood. The cavity magnetron instead created a chaotic dance of electrons spinning in powerful magnetic fields, their motion synchronized by the resonant cavities in ways that were barely understood theoretically. When colleagues from other departments visited the laboratory and examined the prototype, several openly questioned whether the device would produce anything except random noise and wasted electricity. By mid-March, the copper block was complete, its 8 cavities drilled and polished, its central hole ready to receive a tungsten cathode that would emit the electrons needed for operation. Boot had designed an ingenious antenna system, a simple loop of wire that would extract microwave energy from one cavity and deliver it to whatever apparatus needed the signal. The entire assembly measured only a few inches across, small enough to hold in one hand, yet theoretically capable of generating kilowatts of focused microwave power. They had built it with their own hands from basic materials, working from first principles because no textbook described what they were attempting. The final assembly required a vacuum pump to evacuate air from the tube, thick glass to seal the ends, and powerful magnets to create the fields needed to bend electron paths into their dancing trajectories. Randall secured a pair of permanent magnets from a university physics demonstration kit, absurdly borrowing educational equipment for a device that might change the course of the war. They had no sophisticated diagnostic equipment, no oscilloscopes capable of displaying gigahertz frequencies, no standard procedures for testing. They would connect their creation to a power supply, switch it on, and hope their mathematics had been correct. 21st February 1940 became legendary in British scientific history, though the date itself was classified for years. Inside their cramped laboratory, Randall and Boot completed the final connections on their cavity magnetron prototype as afternoon shadows lengthened across Birmingham. They had worked continuously for nearly 3 weeks, machining parts, calculating resonant frequencies, and assembling components with trembling hands. Now the moment of testing had arrived, and both men felt the weight of expectation mixed with the very real possibility of complete failure. Boot checked the electrical connections one final time while Randall positioned a simple detector little more than a neon bulb near the antenna loop to indicate if their device produced any radiation at all. Professor Marcus Oliphant had joined them for the test, his presence adding formality to the occasion. Oliphant understood the stakes perhaps better than anyone. He had championed the cavity magnetron project despite skepticism from established radar experts who believed centimetric wavelengths were impractical for high-power applications. The existing British radar network operated at wavelengths around 1.5 meters, using enormous antenna arrays that could never fit aboard aircraft. German scientists were pursuing similar long-wavelength systems, and intelligence reports suggested neither side had mastered the generation of powerful short-wavelength radiation. Whoever solved this problem first would gain an immense tactical advantage. Boot's hand moved toward the power switch with deliberate slowness. The cathode would heat up, emitting electrons into the evacuated space within the copper cylinder. Powerful permanent magnets would force these electrons into circular paths, and if their calculations were correct, the electrons would bunch together, oscillating through the 8 resonant cavities, generating electromagnetic waves at precisely the frequency determined by the cavity dimensions. If their calculations were wrong, nothing would happen, or worse, the tube might arc internally and destroy itself in a flash of wasted copper and shattered glass. The switch closed. Current flowed. For a heartbeat, nothing happened, and Randall felt his stomach tighten. Then the neon bulb near the antenna blazed with brilliant orange light, far brighter than any of them had expected. The cavity magnetron was working, radiating electromagnetic energy into the laboratory air. But was it generating the right frequency? Was the power output sufficient? Boot quickly moved the detector bulb farther from the antenna 6 inches, then a foot, and still it glowed brightly. They had created something genuinely new, a device that generated radio waves with unprecedented efficiency. Measurements taken over the following hours revealed results that seemed almost impossible. The cavity magnetron operated at a wavelength of 9.8 centimeters, nearly perfect for their intended application. More astonishingly, it produced approximately 400 watts of continuous power from that first crude prototype. Previous magnetron designs had struggled to generate even a few watts at these frequencies. Randall and Boot had achieved a 100-fold improvement using a radical design that conventional engineers had considered absurd. The historical significance of that moment was captured in the research notebooks preserved at the Churchill Archives Centre in Cambridge, which document the mixture of exhilaration and disbelief the team experienced. Yet producing 400 watts in a laboratory was merely the beginning. Airborne radar systems would need kilowatts, not watts, to detect aircraft at useful ranges. The magnetron would need to operate reliably under the vibration and temperature extremes of high-altitude flight. It would need to be manufactured by the thousands, perhaps tens of thousands, requiring industrial processes that did not yet exist. The prototype sitting on their workbench was a proof of concept, nothing more. But it was proof that changed everything, demonstrating that centimetric radar was not merely possible but practically achievable. Britain now possessed the key to night air defense if the technology could be developed quickly enough. 6th September 1940, and an unmarked aircraft sat on a rain-swept runway at an airfield outside Bristol, preparing for one of the war's most consequential journeys. Aboard was Sir Henry Tizard, Britain's chief scientific advisor, leading a secret delegation to the United States carrying Britain's most precious military secrets. Among the items packed carefully in steel cases was the cavity magnetron, the device that Randall and Boot had perfected through the spring and summer months. Britain was sharing its most advanced technology with the Americans in a desperate gamble that would either forge an unbeatable alliance or squander advantages that might never be recovered. The decision to share the cavity magnetron with America had been intensely controversial within British military and political circles. Winston Churchill himself had wrestled with the implications. Britain stood alone against Nazi Germany, its cities burning under nightly Luftwaffe raids, its survival dependent on technological advantages in radar and other secret weapons. The cavity magnetron represented perhaps the most significant leap forward in radar technology. Since the concept had been developed, some military leaders argued that sharing such a device was reckless, potentially allowing secrets to leak to enemy hands through American industrial espionage or careless security. Yet Britain desperately needed American industrial capacity to manufacture these devices in the quantities required. The American relationship with Britain in September 1940 remained complicated and uncertain. The United States maintained official neutrality, though President Franklin Roosevelt had found ways to support Britain through destroyer transfers and other arrangements. American scientists and engineers possessed formidable capabilities, but they had not yet developed cavity magnetron technology. British intelligence knew that German scientists were also pursuing centimetric radar, though apparently without success. The technological lead that Britain possessed was precious but temporary. Within months, perhaps weeks, German engineers might achieve similar breakthroughs. The window for leveraging British radar superiority was closing rapidly. Tizard's mission carried other secrets besides the cavity magnetron details of British jet engine development. Proximity-fused designs, submarine detection systems, and numerous other innovations born from Britain's frantic wartime research efforts. But the cavity magnetron was the crown jewel, the device that made everything else possible. When Tizard's delegation arrived in Washington, they were met with a mixture of enthusiasm and skepticism from American military and scientific leaders. According to accounts preserved in the National Archives in College Park, Maryland, some American experts initially doubted that such a small device could generate the power levels the British claimed. The demonstrations proved convincing. When American scientists at the Radiation Laboratory in Massachusetts examined the cavity magnetron and conducted their own tests, they immediately recognized its revolutionary potential. The device generated kilowatts of power at 10-centimeter wavelengths using a tube smaller than a quart milk bottle. American radar systems still used long wavelengths requiring massive antenna arrays. The cavity magnetron would enable compact radar sets small enough for aircraft, naval vessels, and mobile ground units. It would transform radar from a strategic early warning system into a tactical weapon usable by individual military units. American industrial capacity mobilized with impressive speed. Companies like Raytheon and Westinghouse began manufacturing cavity magnetrons, using the British design as a template. Engineers developed improved cooling systems, more robust cathode materials, and manufacturing techniques suitable for mass production. By early 1941, American factories were producing hundreds of cavity magnetrons monthly, ramping toward thousands. The Tizard mission had succeeded in its primary objective, leveraging British scientific innovation with American manufacturing capacity to create an overwhelming technological advantage for the Allied cause. Britain's gamble paid dividends beyond simple magnetron production. The sharing of cavity magnetron technology cemented scientific cooperation between British and American research establishments, creating collaborative relationships that would prove crucial throughout the war. American engineers introduced manufacturing innovations that British facilities adopted, improving reliability and reducing costs. The exchange flowed both directions, creating a genuine partnership rather than a one-sided technology transfer. When the United States entered the war after the Japanese attack on Pearl Harbor in December 1941, the radar cooperation initiated by the Tizard mission had already borne substantial fruit. 19th March, 1941, and Flight Lieutenant John Cunningham climbed into the cramped cockpit of his Bristol Beaufighter at RAF Middle Wallop as twilight descended over southern England. His aircraft was one of the first British night fighters equipped with operational airborne interception radar using cavity magnetron technology. The bulbous radome under the Beaufighter's nose contained an antenna barely 30 inches across, yet this compact system could detect enemy bombers at ranges exceeding 3 miles, performance impossible with earlier radar systems. Cunningham had been training with the new equipment for weeks, learning to interpret the glowing blips on his cockpit display, while his radar operator, Sergeant Jimmy Rawnsley, called out ranges and bearings from the cramped position behind him. The transformation in night fighting capability was nothing short of miraculous. Before airborne interception radar, British night fighters had relied on ground-controlled interception, with radar stations on the ground tracking both friendly fighters and enemy bombers, then radioing vectors to guide the fighters within visual range. The system was cumbersome, unreliable, and easily disrupted. Fighters often burned through their fuel searching empty sky, while enemy bombers struck targets miles away. The successful interception rate had been appallingly low, perhaps one enemy aircraft destroyed for every 100 sorties flown. British night defenses were barely functional, and German bomber crews knew it. The cavity magnetron changed everything by enabling sufficiently powerful radar small enough to fit in a fighter's nose. The technical challenges had been formidable. Radar engineers at the Telecommunications Research Establishment had to develop entirely new antenna designs, optimized for centimetric wavelengths. They created scanning systems that swept the radar beam across the sky, displaying returns on a cathode ray tube mounted in the cockpit. They designed vibration-resistant magnetron mounts because the devices initially failed under the violent shaking of aerial combat maneuvers. They solved countless small problems through trial and error, each solution bringing operational capability one step closer. That night, Cunningham's radar detected a Heinkel bomber approaching the English coast at 10,000 feet. Rawnsley's voice crackled through the intercom, providing a bearing and range. Cunningham advanced his throttles and turned toward the contact, watching the blip on his display grow stronger as the range decreased. At half a mile, he could see nothing through his canopy except darkness and stars. At a quarter mile, still nothing. Then, at mere hundreds of yards, the Heinkel materialized against the slightly lighter sky, a dark silhouette of wings and fuselage. Cunningham positioned his Beaufighter directly behind and below the German bomber, aimed carefully, and pressed his gun trigger. His 4 20mm cannons roared, sending tracers arcing into the Heinkel's fuselage. The German aircraft shuddered, caught fire, and spiraled downward toward the channel. According to records maintained by the RF Museum in London, that engagement represented the beginning of the end for Germany's night bombing campaign against Britain. Over the following months, British night fighter squadrons equipped with cavity magnetron radar achieved steadily increasing success rates. German bomber losses climbed dramatically. Luftwaffe crews who had previously operated with relative impunity found themselves intercepted repeatedly, their aircraft destroyed by British fighters they never saw approaching. The psychological impact proved as devastating as the physical losses. German bomber crews developed an almost superstitious dread of the British night fighters that seemed to find them regardless of weather, darkness, or evasive maneuvers. The cavity magnetron's impact extended far beyond night air defense. Naval vessels received surface search radars using magnetron technology, enabling them to detect submarines and surface raiders at unprecedented ranges even in storms and fog. Anti-aircraft gun batteries received gun-laying radars that tracked approaching aircraft with precision that made effective fire control possible even at night. The British military was being transformed by a device that had begun as a theoretical sketch on a Birmingham laboratory workbench barely a year earlier. The Germans attempted to develop similar technology, but their efforts consistently lagged behind Allied advances. British and American engineers refined cavity magnetron designs throughout the war, achieving ever greater power output, improved reliability, and reduced manufacturing costs. By 1943, magnetron-based radars had become ubiquitous across Allied military forces, providing a technological edge that German scientists never overcame. 15th July, 1941, and the Metropolitan Vickers electrical factory in Manchester hummed with activity as workers assembled cavity magnetrons on newly constructed production lines. Britain desperately needed thousands of the devices, but manufacturing them in quantity proved vastly more difficult than building laboratory prototypes. Each magnetron required precision machining, careful assembly under vacuum conditions, and rigorous testing to ensure it met military specifications. The copper resonant cavities had to be drilled with tolerances measured in thousandths of an inch. The cathodes needed special tungsten alloys capable of withstanding intense electron bombardment. The glass-to-metal seals had to maintain perfect vacuum despite temperature extremes and violent vibration. The engineering challenges of mass production forced innovation at every stage. Traditional vacuum tube manufacturing relied on skilled craftsmen who assembled each unit individually, checking critical measurements by hand and making adjustments based on experience and intuition. This approach could never produce the thousands of magnetrons monthly that British radar programs demanded. Engineers developed specialized machinery that automated critical manufacturing steps, precision drills that machined all 8 cavities simultaneously, ensuring perfect symmetry. Vacuum pumping stations that processed multiple magnetrons in parallel. Testing equipment that verified performance without requiring skilled operators to interpret complex measurements. Material shortages created constant crises. Copper, essential for the resonant cavities, was desperately needed for artillery shell casings, electrical wiring, and countless other military applications. The Ministry of Supply allocated copper to magnetron production only after intense arguments about priorities and competing needs. Tungsten for cathodes came primarily from Portuguese mines, and supply interruptions threatened production whenever diplomatic tensions flared. Glass suitable for high-temperature seals was manufactured by only a handful of specialized firms, creating bottlenecks that cascaded through the entire production system. Industrial managers struggled to balance quality against quantity, knowing that defective magnetrons could fail at critical moments, potentially costing aircraft and crew lives. The workers assembling magnetrons in Manchester came from diverse backgrounds, many of them women who had never worked in electronics manufacturing before the war. Training programs taught them the essential skills: how to handle fragile components, how to recognize good vacuum seals from poor ones, how to test completed units using specialized equipment. The work was demanding and occasionally dangerous. Magnetrons that failed during high-power testing sometimes exploded, showering workbenches with glass fragments and copper shrapnel. Workers learned to position safety shields before testing and to evacuate areas when tests showed suspicious behavior. Despite the hazards, production steadily increased as experience accumulated and procedures were refined. According to industrial records preserved at the Manchester Museum of Science and Industry, Metropolitan Vickers alone produced over 8,000 cavity magnetrons between mid-1941 and the war's end in 1945. Other manufacturers contributed additional thousands: GEC in Birmingham, Ferranti in Edinburgh, Standard Telephones and Cables in London. American factories outpaced British production by large margins once their assembly lines reached full capacity, with firms like Raytheon eventually producing tens of thousands of magnetrons monthly. The combined output from British and American manufacturers reached truly staggering levels, enabling radar to be deployed on virtually every platform where it could provide tactical advantage. The cavity magnetron production program demonstrated Britain's ability to translate scientific breakthrough into military capability despite operating under the desperate constraints of total war. From Randall and Boot's initial prototype in February 1940 to full-scale industrial production required barely 18 months, a timeline that would have seemed impossibly compressed in peacetime. The achievement required close cooperation between university scientists, industrial engineers, military procurement officials, and factory workers, each group contributing essential expertise. The success validated Britain's approach to wartime research and development, which emphasized rapid prototyping, pragmatic engineering, and close integration between researchers and operational users. 3 June 1943, and the Allied invasion fleet assembling near Southampton represented the largest amphibious operation in human history. Operation Overlord, the invasion of Nazi-occupied France, would depend critically on technologies that had not existed when the war began. Among the most crucial were shipborne radars using cavity magnetron technology, systems capable of navigating through darkness and fog while detecting German vessels, submarines, and defensive positions. The surface search radars installed on destroyers and cruisers could map coastlines with precision that enabled accurate navigation even when landmarks were invisible. Fire control radars guided naval guns with accuracy that would have been impossible using visual ranging alone. The cavity magnetron had evolved considerably since Randall and Boot's initial prototype. Engineers had developed magnetrons operating at different wavelengths optimized for specific applications. 3-centimeter magnetrons provided higher resolution for precision targeting systems. 10-centimeter magnetrons offered better performance in rain and fog for search applications. Manufacturers produced magnetrons with power outputs reaching 100 kilowatts for ground-based systems and 10 kilowatts for airborne applications. Reliability improved dramatically as engineers learned to build cathodes that lasted hundreds of hours rather than failing after mere tens of hours. The cavity magnetron had matured from a laboratory curiosity into a robust military technology deployed across every combat theater. Bomber Command used magnetron-based H-2S radar to navigate and locate targets during nighttime raids over Germany. The system created crude ground mapping images by scanning a radar beam beneath the aircraft and displaying terrain, returns on a cathode ray tube. Cities appeared as bright patches on the display, rivers showed as dark lines, and distinctive terrain features provided navigation references even when cloud cover obscured everything visually. German air defenses eventually learned to detect H-2S radar transmissions, using them to locate British bombers, but the tactical advantages generally outweighed the risks. British bomber crews could find their targets consistently rather than dropping ordnance blindly, hoping to hit something militarily significant. Coastal Command used magnetron radar to hunt German submarines in the Atlantic, where U-boats were strangling Britain's supply lines. Aircraft equipped with ASV Mark III radar could detect submarine conning towers at ranges of several miles even at night or in heavy weather. The surface submarines that had previously been nearly invisible became vulnerable targets. U-boat commanders responded by remaining submerged longer, reducing their operational effectiveness and making them easier prey for convoy escorts. The Battle of the Atlantic turned decisively in the Allies' favor during 1943, and while many factors contributed, magnetron-based radar played an essential role by denying German submarines the surface mobility they required for effective operations. The Pacific Theater saw equally dramatic applications. American naval forces used magnetron radar to detect Japanese aircraft at long ranges, providing crucial early warning that enabled successful defense against kamikaze attacks. Land-based radar systems guided fighter interceptions against Japanese bombers attacking Australia and New Guinea. The technology that had been developed to defend Britain against the Luftwaffe adapted readily to very different operational environments and tactical challenges. Japanese engineers attempted to develop similar capabilities but never matched Allied performance, leaving Japanese forces at a persistent technological disadvantage that compounded their numerical and industrial weaknesses. According to military historians analyzing declassified documents at the Imperial War Museum, the cavity magnetron's strategic impact rivaled that of any other single technology developed during the war. Atomic weapons ended the conflict dramatically, but magnetron radar helped determine who would win the long struggle before nuclear weapons became available. The device that began as an absurd design sketched on a Birmingham laboratory workbench in February 1940 had become an essential tool of modern warfare, deployed on thousands of platforms, produced by the hundreds of thousands, and proving its worth in every operational environment from Arctic convoys to tropical jungles. 10th May, 1945, and across Europe, crowds celebrated Victory in Europe Day as Nazi Germany surrendered unconditionally. In laboratories and factories throughout Britain and America, the scientists and engineers who had developed radar technology allowed themselves quiet satisfaction, knowing their work had contributed materially to the outcome. The cavity magnetron had been among the war's most closely guarded secrets, and even after victory, its existence remained classified. The general public had no idea that a device measuring mere inches across, operating on principles barely understood when the war began, had helped turn the tide of the greatest conflict in human history. John Randall and Harry Boot received remarkably little public recognition for their achievement. The Official Secrets Act prevented them from discussing their work openly, and in any case both men were temperamentally unsuited to self-promotion. Randall returned to academic physics, continuing research on electromagnetic phenomena throughout a long career at King's College London. Boot took up a position at the Service's Electronics Research Laboratory, continuing to work on microwave technology for military applications. Neither man received financial rewards commensurate with the strategic importance of their invention, though both were later honored with fellowships in the Royal Society and other academic distinctions. The patent on the cavity magnetron was classified for years, and when finally released, its commercial value had largely evaporated. The cavity magnetron's influence extended far beyond its military applications. After the war, surplus military magnetrons became available to researchers and entrepreneurs who recognized their potential for peacetime uses. In 1946, Percy Spencer at Raytheon discovered that magnetron radiation could heat food rapidly when a chocolate bar in his pocket melted while he stood near an operating radar unit. This observation led to development of the microwave oven, which used cavity magnetrons to generate the electromagnetic energy that heated food through dielectric heating. By the 1970s, microwave ovens had become common household appliances, though few users understood that the technology derived from wartime radar research. Magnetron technology contributed to development of particle accelerators used in physics research and medical applications. The powerful microwave radiation generated by magnetrons could accelerate electrons to high energies, enabling research into atomic structure and development of radiation therapy for cancer treatment. Communication systems adopted magnetron-based transmitters for certain applications where their high power output and simple construction provided advantages over alternative technologies. Industrial heating processes used magnetrons for applications ranging from drying lumber to vulcanizing rubber. The fundamental principles that Randall and Boot had exploited using resonant cavities to generate coherent electromagnetic radiation from electron streams found applications in numerous fields far removed from the military urgency that had driven the original invention. Modern radar systems have largely moved beyond cavity magnetrons, adopting solid-state transmitters and sophisticated phased array antennas that provide capabilities Randall and Boot could not have imagined. Yet the magnetron's influence persists in the architecture of microwave technology and in the fundamental understanding of how electromagnetic radiation can be generated at high power levels in short wavelengths. The device demonstrated that radical innovations could succeed when theoretical insight combined with practical engineering under conditions of desperate necessity. It showed that small teams working with limited resources could achieve breakthroughs that eluded larger, better-funded organizations when those teams possessed deep physical understanding and willingness to challenge conventional approaches. The story of the cavity magnetron offers lessons about scientific innovation, technological development, and the complex relationship between basic research and practical application. Randall and Boot were not working toward microwave ovens or cancer therapy when they drilled those 8 copper cavities in February 1940. They were trying to solve an immediate military problem using the best physics and engineering they could muster. The device they created achieved its intended purpose-enabling compact, powerful radar that helped Britain survive and eventually prevail. But it also demonstrated something more fundamental, that genuine understanding of physical principles, combined with creative engineering and determination, could produce technologies whose full implications and applications might not become apparent for years or decades. According to the biographical accounts compiled by the Royal Society and preserved in their historical archives, both Randall and Boot remained modest about their achievement throughout their lives, emphasizing the contributions of colleagues and the collaborative nature of wartime radar development. They understood that the cavity magnetron, revolutionary though it was, represented one element in a vast technological mobilization that included thousands of scientists, engineers, and workers. Yet history recognizes their specific contribution as genuinely transformative, the device that made modern microwave technology possible, that helped determine the Second World War's outcome, and that demonstrated how fundamental scientific research could be translated into practical capability when civilization's survival hung in the balance. The absurd design sketched in a Birmingham basement had changed the world.